So we'll come to the main topic of the nonlinear analysis, which is the stability analysis. Okay. So so we saw in the case of a simple pendulum, right? So we had the downward position. So this was the lower equilibrium point, right? So maybe, and then you had the upper equilibrium point, right? There were two equilibrium points, right? And we also saw that we did linearization here. Okay, and also the linearization here, right? So the linearization threw up a saddle point, right? Saddle point has one eigenvalue, so and we saw the phase portrait also. So if you perturb it about that, it will escape from there, right? Now for the downward, the linearization yielded eigenvalues which are on the j omega axis, right? That is, the real part is 0. And then we also saw from the Hartmann-Grobman theorem that now you cannot conclude anything about the nonlinear system based on linearization when you have the eigenvalues on the imaginary axis, right? However, from the physics of the system, you know in some sense, okay, whatever idea of stability that you have, okay, because I have not defined stability, but you do understand your own, in your own physical sense, right, stability. You know that the downward equilibrium point is stable, right, whatever that physical sense may be. But the math has, the linearization has failed us there, right? So we are not able to conclude, right? So conclude anything about the stability of this when you have a center, right? So this is the center based on linearization, right? We don't know whether it is a center for the nonlinear system also, right? But we cannot conclude that because of the Hartmann-Grobman theorem, right? So now the question is, how do we analyze the stability of this downward equilibrium point, right? Because the linearization is of no help to us now, right? So that is the that is where we need to go for, treat the original nonlinear system, and we have to deal with it, right? Linearization will not work, right? So very powerful tool in nonlinear analysis, right? You have x dot is equal to f of x. There is no restriction on the dimension, any finite dimension, right? And then say, without loss of generality, let us assume that the origin is the equilibrium point of the system. If it is not origin, we can always choose another coordinate system and shift it to the origin, right? So I'll just call it the origin as the equilibrium point of interest, okay? And assume that it's an isolated equilibrium point, okay? So if it is not isolated, then there are other notions of step. I will talk little briefly if I have time, but assume that it is isolated equilibrium point, right? So x equal to 0 is, that is in the neighborhood of that, there is no other point, right? So the challenge, so what we want to do? We want to do some stability analysis, right? Of course, we'll define the different notions of stability, but you see the hard part is now linearization is not going to help us, as you saw in this example. So the only information you have is this x dot is equal to f of x, right? you don't have anything else, and we cannot solve the differential equation, right? And this is where, you know, the work of Lyapunov comes into picture, right? He was a Russian mathematician who was studying the stability of the orbital motion, right? And then he came up with a method of analyzing the stability of a nonlinear system. I mean, so the whole of I mean, as I did talk about an important concept called the positive invariance of a set. You will see that here also, and I would say control would have not been what it is today if not for Lyapunov. Okay, so that is how it has influenced control theory so much, right? So there are different notions of stability. So let us define those and understand them. Okay, so the first, so it is called just stability, right? So the origin. So stability, when we do, when we talk about stability, right? Unlike when you were doing a stability analysis for a transfer function, right? You always talked about this system is stable, this system is marginally stable, right? Either you use Bode, Nyquist, or root locus, right? But you see, all that has come by doing some linearization about some point, right? So it makes sense to talk stability always of a point, right? So when I say stability, I have to mention which you are talking about, stability of which point, right? And typically we talk about equilibrium points, right? Or operating points, okay? So stability is always with respect to a point. So it makes no sense to say system is stable. No, right? We have to specify the point, okay? The point, so it's a point definition, okay? So the origin of, so I'll call this as 1 is stable if given any epsilon greater than 0, right, a number, there exists a delta which could depend on this epsilon and also a positive number, such that whenever the initial condition lies in a ball of delta, implies the solution lies in a ball of epsilon for all t greater than or equal to 0. Okay, so let me picture this, right? So whenever you see this epsilon delta, they are like challenge problems. Okay, somebody has given you a challenge and then you have to come up with something, right? So here the challenge is thrown to you is this epsilon number, right? You are not free to pick it up. Somebody, I mean, think it as somebody has given to you, and then it is up to you to come up with this delta and ensure this, right? That means you have to pick up this delta in such a way that for all initial conditions in this delta ball, I mean a ball centered at 0 and with radius delta, that's the meaning of this inequality, right? It's a ball of delta radius and center 0. So for all initial conditions in that, your solutions are trapped in the ball with center as 0 and radius epsilon, right? So this is the trapping that you want, right? So what should be the ball size such that for all initial conditions in this ball size, your solutions are trapped in this, okay? So the picture is like this. So what is given to you is this epsilon, okay? And I am taking about the origin because my origin is the equilibrium point of interest, right? Otherwise, you will have to just shift it to any other if it is not the origin. So this is given to you, right? And your task is to come up with a delta ball, right? Such that for all initial conditions starting in this delta ball, right, your solution is trapped in this. So this is again, that means what? the epsilon ball has to be positively invariant, right? This condition, right, it means that this epsilon ball is a invariant set. You cannot escape out of it because there is for all t greater than or equal to 0, right? Then we say that that equilibrium point, which is the origin, is stable. There is no, you can see that there is no requirement that the trajectory goes to the origin. It can hover around this equilibrium point, right? It can go anywhere in this epsilon ball, but it should not escape out of it, right? In other words, small perturbations around the equilibrium point should lead to trajectories staying in the vicinity of that equilibrium point, right? So it should not, so this stability captures that small perturbations lead to small motions around that equilibrium point. If you find that even a small perturbation will lead the trajectory to go, somewhere and then come back, that is not stability for us, right? Stability is small perturbations lead to small motions along the, about the equilibrium point, right? Now, in honor of Lyapunov, this definition is also known as Lyapunov stability. Okay, so this is the first definition of stability, which just talks about trapping the trajectories in arbitrarily small balls. Okay, if you want to see the time evolution of this, right, then the picture would be something like this. Say if I have just one dimensional, or maybe I have some x1, x2, okay, and this is the time axis, right? So think of again, this is the epsilon ball, right? And then you have to come up with a delta ball, right? So this can just propagate this. You don't have to propagate delta ball because you're just going to choose the initial condition in this delta ball, right? So in this x1, x2 plane, you choose some x0, which is in the delta ball, and so this delta is something which you have to design given the epsilon. So the design should be such that for all initial or any initial condition in this delta ball, the trajectory, right? So the trajectory is trapped in this epsilon ball. It doesn't go out of that tube, right? If you think of a time as the third axis, right? So there's a x1, there's a x2, and this is the time axis, right? So so the propagation of the trajectory should be such that it lies in this tube of epsilon radius, right? So this is the requirement for a stability. Any questions here? Okay, so let us now define the second notion, which is much stronger notion of stability, but maybe I'll define what is meant by attractivity. The origin is said to be attractive if there exists some constant C0, C positive, such that norm of x of t goes to 0 as, it approaches 0 as t tends to infinity for all Okay. So attractivity is saying that, see here I use norm because they could be all vectors, right? My x is in Rn, right? So, and we are talking about the ball, right? So that's why if you remember the way we defined the open ball, right? It was all points in x such that norm of x is strictly less than some number, some positive number, right? So attractivity requires that the trajectories, so you have to come up with some constant c such that for all initial condition in the ball of radius c with center at the origin, the trajectory actually approaches the origin as t tends to infinity, right? So, so the picture would be something like this. And yeah, so you come up with some ball of radius c, right, such that all trajectories starting in this, right, they approach the origin. Okay. Now I have a question. Do you feel this attractivity is a stronger notion or does it imply stability? Yeah, that would be the right question. Does attractivity imply stability? Right, because well, you could convince, it is easy to convince yourself, well, I am going to the origin, right? Here I was required to only stay in the epsilon ball. There was no requirement to go to the origin, right? But here eventually you are going to the origin. So you are tempted to say that this is a stronger notion of stability, right? And the answer is no, right? Why? Because right, let us again use the definition. So you give me an epsilon ball, right? Okay. I will find a C ball, this C ball here, right? Some C ball, or even I could even take it inside also. That will make more. So this is the epsilon ball and you are going to come up with some ball of radius c. Okay, so this is epsilon and this is c. C is for the initial condition, epsilon is for the solution, right? And what could happen? Well, it could so happen that you see that in this definition there is no trapping condition, right? So I'll start from this C ball, I'll go wander, have tea, everything, and then come back. It still satisfies this definition, right? It no way violates this definition, but it violates that definition because you have gone out of the epsilon ball. So mere convergence doesn't mean anything, okay? You could have a system like that, okay? In fact, in my lecture notes, there's an example by name called Vinograd system. You just see that. So in that system, there's an origin, and if you perturb it, it will go all, in fact, it makes a sort of figure 8, okay? So if you perturb it here, it goes something like this and comes back, right? So it will eventually come here, right? But for us, stability means what? You should not only come back, but you should also not wander away too much, right? That is the idea of stability, right? So this is violating the notion of stability, right? But then I can use this definition plus this definition to have something nice, which is much more stronger, right? And that is what we have as asymptotic stability. So the origin is asymptotically stable if it is stable and attractive, both, right? So this is a strong notion now. Now you not only require it to stay in the vicinity of the equilibrium point if perturbed, but eventually you should also go to the equilibrium point, right? So in this figure, it will look like this. So maybe you start somewhere. Eventually you will go to the origin, right? You are not only trapped in the epsilon ball, but it's much stronger that you actually go to the origin, converge to the origin, right? So stability plus attractivity gives you asymptotic stability. Right? Now usually we use the word local here, because this may not hold for all initial conditions. That means your delta ball could be very small. It may not be the whole of Rn. If you can show that you take any initial condition in the plane and all trajectories, so suppose assume that there is only one equilibrium point, right? And then you take any initial condition and all the trajectories approach the origin, right? And then plus you have the stability, then we call it as globally asymptotically stable, right? So maybe I will define. So what you can do is, this is local attractivity, and then you can define global attractivity where this is not restricted to C, it is for any initial condition in Rn, right? So global attractivity plus stability gives global asymptotic stability. Right? So how is the global different from local? Well, all this is same, that the norm of the x of t approaches 0 as t tends to infinity. You just remove this and write for all x of 0. That's it. That becomes a global. So it's a much stronger attractivity property. Yeah. This is the definition. So this is also some like you have to come up with this, right? Then you will get a. So here you want to choose like a delta bigger than this, but then it will violate, no? So obviously your delta ball cannot be larger than epsilon ball, because you see here, that means at t equal to 0 also you should be trapped in the epsilon ball. That obviously means that your initial delta ball cannot be larger than epsilon ball, right? And if you want to challenge, right, throw a good challenge, right? Suppose I am the one who has to find out delta, and if I ask you to come up with an epsilon, what kind of epsilon will you give me? Will you give me a very large epsilon, or will you give me a small epsilon to make life difficult for me? Small epsilon, because you are now required, I am required now to find a delta ball such that for small perturbations in that I remain in that small ball. If you give me a large ball, well, I'll be happy to roam around, right? But you are trying to confine me to a small ball, so it becomes more and more challenging, right? Ah. Chaotic, I don't want to relate it to chaos. Uh, in, in chaotic system, will you have an equilibrium point? Ah. I'm not getting exactly what, which exam. Yes, 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 yes. You mean some other equilibrium point? Yeah, obviously, all this will exclude. Yeah, so all this, if you have multiple equilibrium point, so all this will be very local. You cannot have a global, right? So all your epsilon ball and all, right, will be not containing that other equilibrium point. Yeah, you can do that. Fine. Yeah, and then we have one more definition, which is the strongest definition. Okay, so that is exponential stability. Maybe again local exponential stability. So again, the origin. In all this, I have to write one. Yeah. If there exists constants, all positive constants, some say K, C, R, such that I think you don't require this. Right? So your solution is bounded by an exponential function. That means you should be able to find some K, some C. Sorry, here I should be R here. Right? So R is dictates sort of convergence rate. Okay, very large R will say it is converging very fast. Right? So if you are able to find this K, R, and C all positive numbers, such that the solution is bounded by an exponentially decaying function for all initial conditions in the ball of radius C, right? So this is the strongest notion, in the sense that exponential stability implies, asymptotic stability implies stability, right? So we have the okay, this way is obviously not true. Now you see that in nonlinear setting, you have different notions of stability, right? All these are, they become the same in the linear setting. So in the linear setting, if you talk about stability, you talk about asymptotic stability, exponential, they are all equivalent. Okay, there is no, you show any one of this definition holds, then it means the other also holds, right? But only in the nonlinear setting, you have to be careful. This is the strongest and then the weakest this one, right? So that's why in linear setting you never came across all these stability notions because they are all equivalent. Okay, right. Now the hard part is how do you check this, right? Because we said that we cannot solve this differential equation and I am using a solution here, right? So this definition is of no use to check, right? It's just a definition, just like you have definition for controllability, right? Controllability talks about state transfer. That means does there exist a control which takes you from one state to some initial state to target state using in some finite time, right? It's a definition. How do you check it? All right, you can't check for all possible initial states and possible target set, right? But the nice thing is you have nice algebraic condition, the Kalman rank condition, right? So we need some method, okay, to establish this stability, right? So we'll see that how to do that. Any questions in between? So I'll keep this because we want to solve this problem. So maybe before we go, we actually can solve this problem because using this definition, right, we know how to draw the phase portrait for this, right? So at least locally around the lower equilibrium point, so this was theta and x2 was theta dot, right? So this angle was theta, and the phase portrait for small in the vicinity of the lower equilibrium point, that means for small initial conditions, that means it corresponds to oscillations, right? And we saw that they correspond to what? Periodic solutions, continuum of periodic solutions, right? That means the trajectory sorry, the trajectories are all closed trajectories. They are like concentric circles, right? But they are continuum. So we know this, how to plot this, right? This is not a analytical solution, but we did a numerical construction and we know that they are all closed always, right? Now, can you conclude the stability of the origin? You give me sorry, you give me an epsilon. Give me an epsilon. Okay. So let this be the epsilon ball. What delta I pick up? Little less than epsilon. That's it. Right? So pick a delta. That's it. Because you know that if you pick a delta anywhere inside the epsilon ball, there is a periodic orbit through it, right? And it will be having a energy which is lower than the energy corresponding to the epsilon thing, right? So you, if you start with the lower energy, obviously you will not go to a higher energy, right? So epsilon was a energy, given energy. I chose a delta which corresponds to a little lower energy, right? And we assume that it is not dissipative also. So even if it is not dissipative also, that is fine because my delta corresponds to a lower energy level. So no way I can pump energy into the system. It's an unforced system, right? So now we have a result by Lyapunov stability. I mean, we can conclude that stable, which linear technique did not allow us, right? So you see, so the first tool, of course, of course we use the phase portrait here to get this picture, right? So this is again an indirect way but we could apply the definition and conclude the stability of that. Of course, it is not asymptotic stability because there is no friction in that. So oscillations will keep making oscillations, right? So for example, in this we had this pendulum dynamics, some constant, right? This was the unforced, I mean without any friction. You can add some friction, viscous friction, right? If you add a viscous friction, the phase portrait will look like this. It will become a stable, it will become either stable node or stable focus depending upon those constants. Okay, I mean depending upon this A and B, but it will be a stable. Okay, all the trajectories either they will spiral or they will come to the origin, right? Because there is a dissipation now, so you will go from a higher energy to a lower energy. The downward is the lowest equilibrium, lowest energy point, right? So it will go to that. That also gives you the idea that the energy could be some nice function, okay, to analyze stability. Okay, so we could, you know, talk about this epsilon, delta and all using energy levels, right? So why not generalize this for any nonlinear system, right? At least for mechanical systems, you know the energy of the system, which is kinetic energy plus potential energy, right? So if you find out that the energy of the system is decreasing along the trajectories of the system, then that means things are not blowing up. Okay, so you have some kind of stability there, right? That was the idea Lyapunov used, right? And he came up with a notion called Lyapunov function, right? So we'll see how to actually check all this, right, by constructing something known as a Lyapunov function, right, which is at the heart of stability theory, right? So we did use the phase portrait here. Eventually we will show the stability of the downward equilibrium point using by constructing something known as a Lyapunov function, right? So these are called the Lyapunov stability theorems. Yeah, but before I state this theorem, let us see what all we have with us and what is that we need. Okay, so suppose again take the plane, right? Suppose we have some function. Okay, so say v is from here, in this case R2 to R, a real valued function, and you define it as some x1 square plus x2 square, a quadratic. Okay. So I can plot this function. I can plot the level sets of this for different values of the values, the real values. Okay. So of course at x1 equal to x2 equal to 0, right? V of 0 is 0, right? So you can note down, V of 0 is 0, which is our equilibrium point. Okay. Just the remarks, just keep track of the remarks also. Okay. So so this corresponds to V of x equal to some c, some value of c, some number, some level sets, right? So if you visualize this function, right, on x1, x2, how does this look? Looks like some bowl, right, or something like a, which tapers at the origin, and then it just extends all the way to infinity, right? So this function looks right. And what I have done here, I have taken a section. This value is C, and I have projected it onto the x1, x2 plane, and this is how it looks, right? I mean, this visualization is very important. It will help you to understand what is happening. Now, at any point, how is the gradient? Which direction it points? The gradient points in the direction of where the function is increasing, right? And remember, this is nice closed curve, right? So, in fact, here I have taken something quadratic, right? So, the next remark I want to write here is V is positive. Here you can look at this, right? V is always non-negative, right? It takes all positive values for any x. It is 0 only at x equal to 0. Okay. So keep track of this picture, keep track of the remarks that I am writing here. Okay. And also keep seeing what is happening in this picture. So my gradient will be something. I'll denote the gradient by del V of x. It's nothing but dou V by dou x. But it's a vector here because x can be, here we are taking R2, so it is dou V by dou x1 and right. And I can do this because this is a nice differentiable function, right? So in fact, let me write continuously differentiable. Okay, fine. Now let me do the derivative with respect to time of this function along these trajectories, right? So that means differentiating V with respect to time and I'll make it very clear. Why do I write this such a long phrase, right? For the precise reason that what is this dV by dt is nothing but the gradient of x into x dot, and it's an inner product. It's a dot product, or we call it as inner product or dot product, right? It's a dot product between the gradient and the x dot. This is what? Chain rule. Your good old chain rule, right? That's why whenever you are doing this chain rule, you should write differentiating V with respect to what? Time, fine, but what? Along the trajectories of the system. This part is captured here. That is x dot. X dot captures the trajectories of the system. V has nothing to do with x dot. V is some function, right? How do you relate that? They are related through this dot product, right? That is the derivative of V with respect to time is it is coupling the gradient and the trajectories of the system, right? But what is this? This is nothing but f of x. You know f of x. Somebody has given you f of x, right? That is the model of the system, right? Now what is this? Good old formula. Dot product formula, right? Now suppose this, so you have constructed this function, you did this inner product, and suppose it happens to be positive, right? That means this V dot happens to be positive. What does that mean? It means the angle between the gradient and f of x at this point is acute angle, right? If the angle is obtuse, right? What does that mean? So use another color so that that theta, whatever that theta was, right? So this is f of x. That means what? If you show that your V dot is negative at every point x, right? What does that mean? That means the vector field is at every point pointing inside, right? So let me just this part I am not interested. When it is positive, then I cannot do anything. Okay, of course, if you want to say that does it escape out, then it will be helpful, but I don't want it to escape. I want to get trapped, right? So if V dot less than 0, it implies f of x points inwards. Inverse of what? Inverse of at every point on the curve, at every point on this curve. Okay. The level set. This is called the level set. Right? This is what you want. If you are showing that at every point your vector field is inside, that means if you start an initial condition here, you are trapped forever, right? Now it is not only, you see, if it is negative, that means what? If you come to a little smaller level set, right, it says that you are again negative. That means you are again, all the vector fields are inside. That means what? You are trapped in a smaller and smaller and smaller sets, right? You start somewhere here. Because the vector field is pointing inside, the trajectory is drawn inside, right? Once it is drawn inside, you know that again on any other level set, again the vector field is pointing inside. The only place where it doesn't decrease is at the origin, because there the f of x is 0, because by definition that is the equilibrium point, and f of 0 is 0. So you will go so if you think of V of x as the energy of the system, it is decreasing along the trajectories of the system, and it will become 0 only at the equilibrium point. So that means what? You are not going to move away from that. And if you try to perturb it, right, you will go to some energy level set, some sub-level set, but again the vector fields are pointing inside. Again you will come back. That is stability, right? So if you can show that V dot is negative, right, for all x not equal to 0, then you are done, right? That is nothing but the Lyapunov's theorem. Okay. So Lyapunov stability theorem says that the origin, okay, is Lyapunov stable or stable if you can find a function v, not any function, a continuously differentiable function. Why? Because you are differentiating it. So you need a continuously differentiable function such that v of 0 is 0. That means the equilibrium corresponds to the zero energy. It's like a minima, the minimum point, right? You should not decrease energy beyond that, right? Because that is where you want to go there, right? So such that v of 0 is 0. Everywhere else it is positive, that is v of x is greater than 0 for all x not equal to 0, that is this picture, right? And if it satisfies v dot, right, is negative, okay. In fact, for stability, it can be less than or equal to also, right? If v dot is less than or equal to 0, right, then I don't require this, right? Then x equal to 0 is stable, right? Further, if you show actually v dot is negative for all x not equal to 0, then x equal to 0 is asymptotically stable, right? So what can happen if it is v dot is less than 0? Well, the vector field will be tangential, right? And at the most, what you will be stuck in some level set, right? So that is fine. So what you will do? You are given an epsilon, you will choose such a sub-level set, right? And you will pick a initial condition in that sub-level set. You will be fine because the trajectories at the most they will be tangential to that, right? So you have this epsilon. Somebody has given me this epsilon. What I will do is I will choose a level set, that C, that number C I will choose such that, and I will choose this as my delta ball, right? And I know that on this v dot is what? All the vector fields are tangential. So at the most I will remain in this ball, that's all. And I know that I am trapped forever in the epsilon ball. So I still have stability. If you recall, I don't need to go to the origin for stability. If you have some nice property wherein these vector fields are actually pointing inside, then I will have asymptotic stability, right? So you see, this is the whole geometry of the Lyapunov theorem. All that you require now is what? So what is the hard part in this? Finding the Lyapunov function. So that v is called the Lyapunov function, right? So that is the hard part. But again, for mechanical systems at least, you know the energy of the system that qualifies as a Lyapunov function, okay? For electrical systems, again you can write down the energies of the system, right? Wherever you can write the energy, things are nice. If you don't have the notion of energy, well, try with something like this, a quadratic function to begin with, right? But somewhere there has to be a catch, and the catch is in finding the Lyapunov function. So even for second order system, there is no constructive way of finding a Lyapunov function, right? So you can find, I can give you a second order system and you will never be able to find a Lyapunov function, right? So let us see whether now we can construct a Lyapunov function for the pendulum case. Yeah. Yeah, so you have to be careful because then you should not take other equilibrium points, right? So for the pendulum case, if I am analyzing the equilibrium stability of this, my domain should not include the other equilibrium point. So I will take, for example, for the pendulum, I will take my domain to be, say, 0, pi, open, okay? So this is my theta, this is my theta dot. So you see, this will exclude the upper equilibrium point. So you will have to take your domain appropriately. So whenever you have a multiple equilibrium point, then it fails the necessary conditions for a global asymptotic stability. Global asymptotic stability says what? You start anywhere, you will go to that equilibrium, desired equilibrium point. But what if I have another equilibrium point and if my initial condition corresponds to sitting on that equilibrium point? Though no way I can escape out of it, right? So necessarily for global asymptotic stability, it should have an unique isolated equilibrium point. If there are multiple equilibrium points, the only notion of stability applicable is the local asymptotic stability. You cannot apply global asymptotic stability. So for the pendulum, I can only talk about local asymptotic stability, right? So I have not put on the theorem because I just wanted to illustrate how the theorem is, what are the hypotheses of the theorem, right? And all that I have shown it on this figure, right? Any questions? Any other questions? No, that also is very, I mean, even though it says constructive, it doesn't guarantee. It's a very, for a very specific, you know, something like, it doesn't work all the time. It doesn't work all the time, right? Pardon? Just do the change of coordinates, that's all. Choose a new coordinate so that in the new coordinates is the origin. Okay, there is nothing holy about this origin. It's just for our, you know, simplicity. We will assume, you know, that it is origin. If it is not origin, you shift it. That's all. Yeah. So those conditions will become V at x e equal to 0. Then V x is positive for all x not equal to x e, right? Then V dot is less than 0 for all x not equal to xc and equal to 0 if and only if x equal to xc. I mean, perfectly carries over. Right. So let us construct the Lyapunov function for the pendulum. So we saw the energy of the pendulum consists of rotational kinetic energy and a potential function, right? So our Lyapunov function also should capture that, right? It cannot be simply a quadratic function. It should capture the potential function also, right? So what is your guess? What was the energy of the pendulum? It was half theta dot square, right? Plus mgl cos theta something, right? So that should motivate now. I can take always some positive constants here, right? And this was what, x1. I can even take k1, k2, where k1 and k2 are free. Free means you can choose whatever you want, provided they are positive. Okay, it doesn't. So you see, this captures is like an energy-like function for the pendulum, for the simple pendulum, right? When you choose this k1 and k2 appropriately, you exactly recover the energy of the this one of the pendulum. Okay, so let us check whether so downward was what. So yeah, x2 equal to 0, x1 equal to 0, right? Yeah, we'll take we'll neglect that friction, or we can even take the friction also. Okay, let us do with this. Okay, so V at x1 equal to 0 and x2 equal to 0 corresponds to downward position. So x1 equal to 0, this will be 0, this will be 0, right? So we have V of 0 is 0, right? So this property holds. V is continuously differentiable, right? That is also fine. But before this, V has to be defined on, yeah, so you should exclude this pi. Okay, so this is your domain. This is your domain, right? So you see that in this domain, the other equilibrium point is ruled out. That is x1 is equal to pi and x2 equal to 0, right? So this is continuously differentiable. And then is V of x positive for all x not equal to 0? Well, yes, you have a positive quantity. This quantity is at x1 equal to 0 is 0. At any other x1, it is a positive quantity. If you just plot the potential function, what will be that? So it is 0 here, and at pi by 2 it is 1, and at pi it is 2, right? So this function is, right? So at least in the interval 0 to pi, I think I can take this to be minus pi to pi. Yeah. So minus pi to pi, this is positive, right? Plus you have this also, which is a positive function, right? So this also holds, right? And what we have to do is we have to find out this V dot, right? So what is V dot? It's the gradient of V, which is okay. So this is K1 x2 this is a sign indefinite term. I cannot fix the sign of this. Okay, if it was x1, it is nice. x1 into sine of x1 is nice positive function in at least minus pi to pi, right? This is a sign indefinite term. So what I do, I will kill this term by appropriately choosing k2a equal to k1. I am free because my k1 and k2 are free constants. So I can choose them to kill this term, right? And what I am left is, which is negative. This is called negative semi-definite. So you need the notion of positive definite and negative definite, negative semi-definite, right? But this is not negative definite because it is only, that means for any x1, right? Any x1, but I mean this is 0, okay? For any x1 not equal to 0 also, but x2 equal to 0. So it is not negative definite, but it is negative semi-definite, right? So anyway, there are little technical things. I don't want to go into that, but at least you have this. You agree, right? This can be at the most 0, right? It can never become positive. There is a minus b k2 x2 square. You agree with that, right? So this is a nice thing that we got by clever choice of the function, right? So you have a V dot which is negative semi-definite, right? And by Lyapunov stability theorem, x of x equal to 0. So by Lyapunov stability theorem, x equal to the origin is Lyapunov stable. So we have a complete analytical stability solution now using the Lyapunov function. This does not use any numerical construction, no phase portrait, no linearization, right? All that you have to do is find the right function. So the Lyapunov stability theorem is a sufficient condition. That means if suppose if suppose it so happened that whatever V you took and you could not get V dot negative, the right hand side is, I mean the V dot is not negative, you cannot conclude anything, right? So they are only sufficient condition. If it is negative, yes, please go ahead and conclude, right? But if you cannot that means there may exist another function which could be negative. So all that you have to do is keep searching. Now, you may also see that I have added friction, but I am showing a very weak property. With friction, what will you expect? The pendulum will eventually come to rest. That's what happens in your home clock, right? I mean, the old pendulum clocks, right? But what did we show? We show only stability. That means we are able to only show that it will hover around the lower equilibrium point, right? So what do? So either you tweak this, right? Find out another Lyapunov function which gives you negative definite function, okay? That may be little hard. You can find it, but in general it may be hard, okay? So there is another result which is known as Lassalle's invariance principle. What does that say? It says that even if you have V dot which is negative definite, you can still do some signal chasing. I mean, you can chase the signals in the sense x1 of t, x2 of t, and so on. And under certain conditions, if they meet certain conditions, you can actually conclude asymptotic stability, right? So for the pendulum, actually you can do that, but we will not go into that. So you can relax the requirement that even V is positive definite, okay? You can relax that to positive semi-definite. You can relax V to be not necessarily negative, but negative semi-definite, and still infer asymptotic stability, right? But that is little, some more work has to be done, but it can be done. It's not a big issue, right? Yeah. Any questions on this? So as I said, I did not write the full theorem, but I think this picture is very important. Okay. This picture also tells you how to show positive invariance, right? If I give you a dynamical system and I give you a set and I characterize it, right? And suppose I can, if that level set happens to be some nice closed curves, right? Then what you have to do is you have to show that along all the boundary of this set, right, the vector fields are all pointing inside. So you have to construct something like a Lyapunov-like function for that, right? So, so if you remember yesterday in the Poincaré-Bendixsen's theorem, one of the requirement was you need a set. It should not contain any equilibrium points, or if it contains, it should be either unstable node or unstable focus. Second condition was it has to be positively invariant. To show that, you can still again come back here and use the same techniques, right? So, yeah, I mean there's more to it, but I think this is the essence of Lyapunov stability, okay? As I said, if you have continuum of equilibrium point, what is the right notion of stability, right? Then if you have a time varying system, what are the stability notions, right? I mean, there are many things to it, but the essence of that is all in this picture here. That is what I'm talking about. So any questions? I don't want to go further because maybe I think I can solve one more problem or something. That maybe, yeah, I can solve a problem, another problem. So maybe I'll also put down this definition of positive definite and semi-definite, and then it will be easy for us to. Okay. So a function v is said to be positive definite if v of x is positive for all x not equal to 0 and equal to 0 when x equal to 0, right. So quadratic function that I have put there is one example. You do encounter this in when you are dealing with matrices. So you say a matrix, symmetric matrix is said to be positive definite. I think it is if and only if obviously when x equal to 0 should be 0, right. So this is what you would have used in some of you might have used it, the positive definite matrix. That means you associate a quadratic with it, and so you have a function. This is a now real valued function, and then just apply this definition. So if you replace this strict inequality by inequality, it becomes what is known as positive semi-definite, right. And then if you reverse the sign, it becomes a negative definite and negative semi-definite. Okay. So for example, v from R2 to R, v of x is say x1 square. Is this positive definite? No, because it is positive semi-definite. It is not positive definite because it is even 0 for x not equal to 0. For example, all points of this point, of this form, where x2 is not 0 but x1 is 0, this is 0, which does not satisfy the definition of positive definite. However, it is positive semi-definite, right. So you have to be just careful about that. Yeah, maybe I'll do one more example. Okay. So there is only one equilibrium point, that is the origin. And we want to analyze the stability of the equilibrium point, right. As I said, all these stability notions are with respect to points, equilibrium points, right. So what is the v that you will take? If you take, right, the problem is you will get maybe by 2, so you will get right. You see this both are signed indefinite terms. It doesn't help, right. Just make this tweak, and now let's see what happens. So I took a quartic in x1 and quadratic in x2. So this will be maybe I have to take kill this 5. Okay, so this both get cancelled, and I have so it will be stable. Even let us take this example of which we encountered. We drew the vector field plot. The origin is the equilibrium point. So for any x positive, x cube will be positive and there is a negative, so the vector field will point all towards the origin. X negative also, the vector field will all point this, right? You can construct just quadratic for this, right? And which is negative definite because it's first order, right? You got x to the power 4, which is negative. Therefore, x equal to 0. In fact, there is no other equilibrium point, right? You take any initial condition, they will all approach the origin, plus the origin is stable. So, in fact, x equal to 0 is globally asymptotically stable, which your linearization fails to conclude anything, right? Yeah, so again, as I said, the hard part is finding the Lyapunov function. Okay. So, any questions? Any other questions? Ah. I don't remember any example like that. Not stable. Oh, okay. It was, yeah. Yesterday we did that. Yes. You remember we had 3 equilibrium points. This, no. There was one problem where it did throw up something like this. The linearization did throw up like this, and then there was some epsilon also parameter sitting in that. So for epsilon positive, in fact, from the phase portrait, it turned out to be that the origin is stable focus or something. You reverse that epsilon. See, okay, to give a quick idea, if you know something is stable, right, and you want to construct a unstable, just reverse the sign of the right hand side, minus f of x, go negative in time, right? So for the pendulum, right, it will become unstable because you are going in negative time, so it will be unstable.